Log on, tune in, find out. Another good idea from Cambridge.
Francesco Calogero from Rome, La Sapienza. We'll be talking on recent findings on isochronous and integrable dynamical systems. Can they somehow be extended to discrete-time evolution?
Okay, it's a pleasure to be here. Thanks to the organizers for inviting me. And let me say immediately that the second part of the title has a question mark. When one gives a talk with a question mark, one usually then gives an answer to the question put there. I'm not going to do that. This is a real question put to all of you and all of us. Maybe at the end I will mention possible ideas, but next, let me go through the abstract. You may have read it, but let me go briefly through it so that you have an idea of what I will cover. So, abstract says that any autonomous dynamical system can be extended or modified, and I will explain the difference in a moment, in a while, between extending and modifying a dynamical system. And in this manner, one obtains a new autonomous dynamical system which involves a constant t. The constant t you put in by hand, so it's an arbitrary free constants that you put in by either modifying or extending the system. And the new modified system will have two properties. The first property is that all the solutions of the new model are isochronous. So they are also, the model is, I call it isochronous. All the solutions are completely periodic in all degrees of freedom with that period t. So you might think this is a very trivial system. Well, as you will see, it need not be trivial and simple at all, even though it will have this feature. All solutions completely periodic in all degrees of freedom with a fixed period. And the second property, and that already indicates that this cannot be so simple, is that if you start from generic initial data, the time evolution of the new system over time intervals short with respect to this period t will be essentially identical to that of the original dynamical systems up to a constant rescaling of time and up to corrections of order 1 over t. So order of the time period you look divided by t. So these findings entail that in some sense, first of all, isochronous systems are not rare because as you will see, given almost any system, you can manufacture a system which is isochronous. So in this sense, they are not rare. They are rare, maybe if you think of physics, because the phenomena which are isochronous are to some extent rare. Although I will hope to put a bit of doubt in your mind with this talk. Maybe often the isochrony maybe is not rare. Maybe it is there all the time, but we'll see. And moreover, it is clear from what I've stated that isochronous systems may feature an extremely complicated dynamic. And this is, at least for me, it was a surprising finding. It may be surprising for some of you. It is also a little bit disappointing because I always thought that integrable systems are in some sense simpler, nicer. They have an evolution which is simpler, but as I will convince you, this is not true. You may have systems which are integrable, in fact super integrable, in fact even more than super integrable, because isochronous systems are more than super integrable, but nevertheless they can be very, the dynamics that described by them can be extremely complicated. All these findings are also valid in the context of Hamiltonian dynamics, in which you start from an Hamiltonian system, you modify or extend it so that it's still Hamiltonian. And so all these properties will be also true for Hamiltonian systems. and I won't repeat them, what is stated here. But I should say that all these the findings I will be talking about have been obtained together with the colleague, Mexican from Switzerland, François Leivras. Some of them are reported in my monograph, which came out about a year ago in February of 2008, but several of the things I will talk have been obtained later, so they are not quite in the monograph. In a sense, it was unfortunate that I wrote this monograph just, well, at the time when we obtained new results. Maybe a second monograph should be written. But I will give, at the end of the talk, references of this, where you can find these new results, several very recent papers, some in press, some to the, well, just came out. And as I already said, the issue of somehow extending this result to discrete time evolution is open. But it is, of course, natural. This is an advertisement of my book. And so let's get started. So first I will describe a trick to transform a dynamical system into an isochronous dynamical system. And as you will see, the trick is very, very trivial and simple. Then the implications will be also simple, but a bit surprising. At the beginning, I will talk in general about dynamical systems. Then I will talk about Hamiltonian systems. So a dynamical system, the most general one that you may think of, is written here. The notation, I hope, is clear. Big X is a vector. This is an arbitrary function there of the vector. But the only restriction here is that I'm considering an autonomous system, so no explicit time dependence. And then, starting from these systems, one can modify or extend it. I will, in a little moment, explain the difference between these two notions, so that now you have a different system, a new system, which is written down here. You see the difference is that I put in front this tau dot of t. Here, of course, the dot indicates a derivative with respect to time. By the way, in this talk, I will be always talking about the real time. There are some tricks to introduce the isochronous system which go through complex time. I will not be talking about them in this talk. So time will always be real time. And so that is the change, that you have this term in front. I will assume that this function tau of t, scalar function tau of t, is periodic with this period t, so which I put in by hand. So this period t is there. This is assumably periodic. And then it is, you see, aside from, independently from this property, if this is true, if this new model is related to the previous one in this way, it is obvious that the solutions of this new model will be given by this formula. You see, where now you have to think of this, I rewrite it in this form, so that you have x of tau. Prime here indicates the derivative with respect to tau. This is the same system written there, but with this new variable tau. And the solution of this system is x of t is x of tau of t. And this is, I think, clear, because when you differentiate this with respect to time, you have this differentiated with respect to, when you differentiate small x with respect to t, you have big X differentiated with respect to tau times tau dot, and so you have this model. So just you have just made a change of the time variable, but not constants. And if tau of t is periodic, then it is clear that x of t will inherit this property. All you need is that the solution of this model, or if you like, of this model as a function of tau, exists for all time, and we assume that this is always true. but nothing more, no integrability, no properties of this kind, no analyticity in continuous time, just existence for real time and uniqueness, of course. And then the consequence will be that if this function tau is periodic, this then will also be periodic. Incidentally, I will not talk about systems which are asymptotically periodic, but you may easily understand that if this functions tau of t does not have the periodicity property, but it has it only asymptotically as t goes to infinity, this will be again inherited by this. So in this way you can also manufacture systems which are asymptotically isochronous, namely only asymptotically they become periodic with a fixed period. One could make this notion more precise, but this is it. Okay, so I have convinced you that now that this system, this new system is periodic, is isochronous. It satisfies this property for all the components, provided tau had that property. So this is the new modified system, but now of course you will tell me that this new system is not isochronous because it has the equation of motions have an explicit time dependence. This tau will be a periodic function of t, so you see the periodicity, you see it there. Well, then there is a second trick, which is again extraordinarily trivial and simple. I am going to discuss systems and modification in which instead of looking at this dynamical system, I look at this dynamical system here, where you see I have replaced tau dot with phi. But of course, if phi is equal to tau dot, evolves in time just as a tau dot, having the right properties, these two systems are the same. But now I will think of this as a new dynamical system, autonomous, with no explicit time dependence, because phi will be, and here there are two possibilities. I can consider phi as a new dynamical variable, and then I will extend this system so that phi will evolve indeed in such a manner that if I say phi of t equal tau dot, then tau will be periodic. So that's the extension. I am extending the system. Typically, maybe I can extend it with one or two more equation of motions involving phi. Or, and that's what I like to call modification, I could take phi to be a function of the variables x, of the dependent variables, such that the system itself will guarantee something of this kind. And this will be clear with an example in the second part of the talk, where I will show you how to apply this kind of trick to what I like to call the most general many-body problem, so a model of great physical significance. Okay, but now I will show you one possible way. I will not, in fact, show you. I will show you just an example, because I want to show you an example that one obtains by taking a model and then extending it by this trick in which you have more dependent variables, and just by showing you an example where this happens. The way you do it is that you do exactly this. You have equation of motions for maybe phi and another variable, and then you make some extra changes of variables so that the model that you will see in a moment does not obviously have isochronicity. In some sense it is nicer. So next is, one can get many examples. There is a paper by Levras and myself in which we give many examples, which is in press in the Journal of Nonlinear Mathematical Physics. I just show you one example. These are the words of what I've said now. This is the example. And so this is now a system of 5 first-order coupled equations. There they are, 3 x's and 2 y's. and it's a simple nonlinear system. It contains this constant omega. It contains 4 constants: alpha, beta, gamma, arbitrary constants, and then this omega. Let's assume they are all real, and when I have an omega, I will have a period t, which is just 2 pi over omega. And now, first, my statement is that this is isochronous. All the solutions of this model are periodic with this period t. And I will maybe convince of you this in a moment when I will show you how you can write the solution of this system. But before doing this, let me make an observation. Suppose I want to look at this system in some sense contained inside this system, which is isochronous, and therefore it is superintegrable. I'm using the term superintegrable even for non-Hamiltonian systems because it has a sense there. It just means that you have the maximal number of conserved quantities. So in this case 4, because the maximal number compatible with the dynamics not being completely freed. So this system has 5 dependent variables, so you would have 4. Of course, it's not Hamiltonian because the number of variables is odd. But so this system is isochronous, therefore it is superintegrable, and for all values of the parameters. But in particular, now let's for a moment look at what happens if I look at what you might think is a subcase of this model when omega is equal to 0. When omega is equal to 0, of course, it will not be anymore periodic. But in some sense, the case omega equal to 0 is contained in this general model. Well, if omega is equal to 0, then there is a subclass of solutions of this model which are y2 equal to 0, because then this solves this equation if this is not there, and also y1 equal 1 over x1, because then if this is not there, y2 is 0. In fact, omega is 0 and y2 is 0. If you now look at this equation with this solution, you will see that it coincides with this one, because if y1 is 1 over x1, this piece in front of the equations disappear, and then this equation essentially coincides with this equation here. You just have to take y1 equal to x1. So in that particular, there is this subcase of solutions which are just the solution of these 3 equations with y2 0 and y1 given by this formula. And now these 3 equations are just the equation of the celebrated Lorentz model. I rewrite them here by, these are the same equation I wrote before, except that I now consider this big X as function of a tau rather than, and so I indicate prime the derivative. So this is the Lorentz model as a function of tau, and you of course know that the Lorentz model is an example, the typical example of a chaotic system, non-integrable, having a chaotic dynamics. And it's contained in the previous system, and in fact, the previous system, the one I've shown these 5 equations, the solutions of this system I can write in terms of the solutions of the Lorentz model in the following way, and this is an exact result. The solution of that model are given just by these formulas. The 3xn are just the big xn, so solution of the Lorentz model, where in place of the argument here is tau of t, and tau of t is this very explicit function, sine and cosine, so it's absolutely periodic as a function of omega. And then in addition, y1 is and y2 are given by this formula. So this is the general solution of the model I wrote you above. It can be written explicitly, but of course it can be written explicitly in terms of the solutions of the Lorentz model, which you don't know how to write, and you don't expect to be able to write them because the Lorentz model is chaotic. So, but this function exists. You can prove that they exist for all time. So that is one type of example, and it already shows you first indication that you may have a superintegrable systems, but its dynamics can be quite complicated because it, in some sense, contains the dynamics of the Lorentz model. However, you see, tau of t is this periodic function. So, in fact, you are only exploring the dynamics of the Lorentz model over a finite interval of time. And so you just follow the dynamics of the Lorentz model, but you follow it back and forth in this tau. That's the basic mechanism of all these results. And so, in a sense, there is no contradiction because the notion of chaos always requires to look at the system over an infinite time. So this Lorentz system is chaotic with definition of chaos that have to do with looking it for infinite time, but this system, this small x, is corresponds to the Lorentz model, but always over a finite time. So that is compatible with the fact that this is not chaotic, but it is, in fact, superintegrable. On the other hand, this period is a period that I've put in by hand. So this period t that I have there can be arbitrarily large. And so this system I've shown you, the 5 equations, can have a dynamics that over a very long time will resemble the dynamics of the Lorentz model. And so it can be very, very complicated. But nevertheless, eventually, then it goes back and it is periodic. And you already here, you get the indication that you see, if you look at times which are short, so with respect to this period here, this tau becomes more or less, becomes essentially linear in time. Tau of t, instead of being sine and cosine, it's linear in t, and therefore it is the second feature that over short period of times with respect to this period t, the dynamics of the new superintegrable model is essentially the same up to a time rescaling to the dynamics of the model you started from, which can be very complicated and non-integrable one. So that's the message. Now, the rest are variations, are other examples, if you like. But the second result I would like to give you is how to embed an arbitrary Hamiltonian dynamics in a superintegrable Hamiltonian dynamics. Something along the line of what we saw, but now we are talking about Hamiltonian dynamics, and I will show you how this can be done. It's very simple. A little less than 10 years ago, I think, it was discovered by Bolsinov and Taimanov an example of this happening. They had a specific system, a geometric system, I think of surface involving 3 variables, which was integrable. But if you looked at a special manifold contained in this integrable geometry, on this manifold the dynamics was non-integrable and chaotic, and this was remarkable. And Sasha Mikhailov told us last year, in Mexico, in fact, in November, December, of this result, and then we realized, in fact, more Francois than myself, that it was easy to understand this result in the framework of what we had done, and in fact, it was easy to generalize it, and the generalization is exactly reflected here. You can take an arbitrary Hamiltonian system and you can embed it inside a superintegrable one. And there is a paper which has that title almost exactly, which has just come out 3-4 days ago in the Journal of Physics A. So you are still in the grace period in which you can even download it freely for 1 month, even if you are not in a university. All right, so now I will prove this for you, and the proof will also make clear what is the meaning of this term embed, we are now in the framework of an extension of a model, and the proof, as you will see, is very simple. So first I state a lemma, and then I prove it. It's very simple. So now I assume I deal with three Hamiltonian systems. I have first an Hamiltonian big H of the variable big P and big Q, so it's an Hamiltonian of just 1 degree of freedom system. Well, I have it there. Then we'll see that we require some property of it. And then I have a second Hamiltonian, small h, of the vector variable P and Q. This is an Hamiltonian that has an arbitrary number of degree of freedom, so let's call big N this number if you like, but it's a system with an arbitrary number, and this will be a completely arbitrary Hamiltonian. And now, out of these two Hamiltonians, I manufacture a third Hamiltonian in this manner. The tilde over these variables is simply a reminder that their evolution is now determined by the new Hamiltonian, which I called H tilde. And you see, it's a very simple construction. You take this this Hamiltonian H, and then I will tell you what properties I will require of H, and you just, in place of P, you put P plus H, the new Hamiltonian, which is a function of P and Q, and then the Q remains the same. And now I have a new Hamiltonian, which is, if this had n degree of freedom, big N, say, now it has n plus 1 degree of freedom. And I assume, of course, that these canonical, the big variables and the small variable are all canonical variables, and they are dependent canonical variables. So they will commute. So as a consequence, this H in the dynamics of H tilde will be a constant of the motion, of course, because this will commute with the other variables, and therefore it will commute with the Hamiltonian. Okay? And then the lemma that I will prove in the next transparency is that the solutions of this model, the small p and q solution of this model, can be written by this formula, where p and q are the solutions corresponding to the small Hamiltonian, which is arbitrary, but I assume that it has solutions, and except that in place of time you have to put the q tilde, which is the q tilde whose dynamics is determined by this. So the dynamics for the variables small p and small q, n of them, produced by this Hamiltonian, defined in this manner, is given by these formulas. Okay? So, and then we'll see the consequences if we make an appropriate choice for big U, H. But first I have to prove this. The proof is absolutely elementary. You write the equation of motions for for these variables. So first the equation of motions for the big P and the big Q. There they are. Just you see, remember what was the Hamiltonian. The Hamiltonian is just this H, which depends only on P and Q, and when you have to find this equation for the P's and the Q's, this is a constants of motion, and so the equation of motion are very, very simply obtained. There they are, depending, this is Hamiltonian, and these are the equation of motion. And now let's look at the equation of motion for the small variables, which are written here for all values of n, and let's maybe go back again so that you see how it goes. When you have to find the equation of motions for the small variables, you have to differentiate this h here with respect to small p or small q, which are inside here. So first you have to differentiate with respect to the p variable, which is that one here, and then you differentiate the Hamiltonian with respect to those variables. So you will have an equation of motions which would contain in front the derivative of h with respect to p, but the derivative of that should be in front here, but the derivative of h with respect to p is just this from the previous equation of motion. So this is what you have, and now you see you have immediately this mechanism that you have in front here, this q tilde dot there, and so this implies that what I wrote before is correct, the lemma that the evolution produced by this new Hamiltonian h tilde for the small p's is just the evolution produced by this Hamiltonian h here for the p's, except that you replace the time with the q of t. And so because the Hamiltonian for the p's without the tilde is just that produced by the h's, and so it's here. So this is now proven. So the lemma has been proven. Sorry, let me go back. So that's the lemma, simple proof. And now, of course, the question is, if we will make a choice of h such that this evolution of the q's will have properties that will entail these results. And what is it? Well, we now choose h, this h of big P and Q, which depends on these two canonical variables. We suppose that this has the following properties. When P is 0, it yields this simple solution. So P equals 0 is a constant manifold, a manifold on which the system P remains 0, and Q just evolves as time. On the other hand, of this manifold, I will require all these solutions to be periodic. So this is a property of this Hamiltonian H. Can I manufacture such Hamiltonians? Yes, of course. It's very easy, and I will show you explicitly an example. But for a moment, assume that the Hamiltonian H has this property, that on this P equal 0 is a constant manifold. It's a manifold on which retains P equal being 0, and Q of t is just this, and then everywhere else it satisfies this property, and then we have proven what we wanted. We had what we wanted, because now the corresponding Hamiltonian H tilde, which is here, will produce a dynamics in which the solutions are just this for P. But then you see, if you now go on the manifold where this is 0, which is just a constant manifold for this Hamiltonian, where P is 0, then Q will be just linear in time. So the evolution of the small p's will be exactly the same as the evolution of these p's produced by this Hamiltonian, which is arbitrary. So we have, for the evolution of this Hamiltonian contains a manifold on which the evolution is just the evolution of this completely arbitrary Hamiltonian. But everywhere else, BQ is periodic, and therefore P's and P tilde and Q tilde are periodic. So everywhere else, this Hamiltonian here has an evolution which is isochronous, and therefore superintegrable more than superintegrable. So that is essentially how you can embed an arbitrary Hamiltonian inside a superintegrable Hamiltonian. You see that relation there, which was P equal to 0, is such that it identifies an invariant manifold of the tilde Hamiltonian, and when you are off this invariant manifold, so here, then the system is periodic. But when you are, because of what we have just said. But if you are on that manifold, then P0Q is linear, and and then I should have gone ahead. When you are on that manifold, namely for initial data that satisfy this condition, and then this condition will be maintained for all time, because it was a constant of the motion for the Hamiltonian, then the evolution will be just this for the tildes, which is exactly the same as the evolution for the, produced by this small Hamiltonian. So this explains in which sense one is embedding the arbitrary Hamiltonian H inside this Hamiltonian H tilde, so that it has this property. The Hamiltonian H tilde is super integrable, but there is one particular manifold in the phase space of this is enlarged phase space, it has n plus 1 degree of freedom, on which the dynamics is that of the original Hamiltonian. I have still to show you how you can construct a function, an Hamiltonian H that has the properties specified in the theorem. So you want one that p equals 0 is a constant manifold, and q corresponds to q equal to t, and any Hamiltonian that has this property will satisfy this. The derivative of h with respect to p for p equals 0 should be 1, and this should be 0. And then you want that the trajectories be periodic everywhere else, and you can manufacture this by, for instance, this very explicit Hamiltonian here, h of p and q, just this explicit Hamiltonian here, and that you, if you like, you can solve it exactly, and you see that big Q and big P are periodic function of t, sine of t, cosine of t, sine of t, so they are periodic functions of t everywhere, except when theta is 0, this h, theta is connected with the value of the Hamiltonian, which is a constant of the motion. I'm looking in the case in which this constant is, the Hamiltonian is less than a quarter. And if it is 0, then theta is 0, but then theta is 0, the cotangent diverges, the sign vanishes, and so q of t becomes just t plus t0, and p becomes just 0, because this is 1 minus 1, okay? So when theta is 0. So it is, this Hamiltonian has the required property. So in this way, one has shown how to embed an arbitrary Hamiltonian, the Hamiltonian H tilde, inside the Hamiltonian small h, inside the Hamiltonian H tilde, which is isochronous, therefore superintegrable, more than superintegrable in some sense. Okay. Third part of this talk, third and last part of this talk, this will be, so to say, more physical, if you like. So it's another trick to modify a Hamiltonian into an isochronous Hamiltonian. Now we are talking about modifying, namely, we start from an Hamiltonian and we do not add additional dependent variables. So we have the same number of dependent variables, and one way to manufacture in this way an isochronous Hamiltonian is the following one. Suppose I have an arbitrary Hamiltonian H. This is now arbitrary Hamiltonian of n degrees of freedom, and suppose I can find a collective variable depending on the canonical variables and momenta, such that this is the standard Poisson commutator of h and theta is equal to 1. Suppose that one can do that. This means that under the dynamics produced by h, this quantity theta will essentially evolve just like time. Because, well, this restricts the category of Hamiltonian that we can look at, but it's not a very big restriction. And then I claim, and I will not prove it because the proof is very, very trivial, but I will rather focus on an example which I'll discuss below. I claim that the Hamiltonian H tilde defined in this way is then isochronous. All solutions are periodic with period 2 pi over omega. So being isochronous, it's also superintegrable. So isochronous Hamiltonian systems are not rare, again, because you can do this trick. And let's look at an example. And for the example, I will prove this result. But the example is very physical, and it's what I call the most general many-body problem. Now, this is the standard Hamiltonian of the many-body problem. This is the kinetic energy. This is the potential energy. And if you look at the kinetic energy here, you will notice that I put all the masses, or we put all the masses equal to 1. But that is an irrelevant simplification, just to write things in a simple manner. And also, from the way I've written here, it looks as the ambient space is one-dimensional, because otherwise I should have put here the square of the vector p. Again, this is an irrelevant simplification. It's just to write the equation in slightly simpler form, but it is obvious that I could deal with particles with different masses and work in a space of arbitrary dimensions, in particular 3 dimensions, like the space maybe we live in. And n is an arbitrary constant. I'll say something about n in a moment. The potential energy V of Q instead does satisfy one restriction, very physical, and this is that it should be translation invariant overall. V is an arbitrary function of the Q's, so it can be 2 body forces, it can be many body forces, arbitrary form of the forces, but it should be overall translation invariant. So essentially only internal forces, not external forces. Okay, and let me say something about n before we go ahead, and I just say that n is arbitrary, but you should keep some values of n as in mind as interesting ones, and the values of n that are interesting ones. One is n equal 2, because for n equal 2, this model is exactly solvable in general. It's essentially 1 degree of freedom. So we'll see examples in which you can solve everything. Another value of n, which is not a value, but the range of values of n, which are interesting, is say n equal 10 to the 23, because then you will be talking about a macroscopic object. For instance, a very good example would be, say, a gas of particles which molecules that interact with, say, Lennard-Jones potentials, and maybe within some confining potential in addition among the particles, so that it would be a confined system with Lennard-Jones forces, repulsive at short distance. I will always assume that the solution exists. In such a case, the solution would exist for all time, no problem. Of course, it would be rather complicated, and but then, as you know, the way out of the complication is not to look at the specific evolution of every molecule, but to have statistical mechanics, thermodynamics, and all these results. So this Hamiltonian subtends all these results in physics. The third interesting case that you should perhaps keep in mind is n of the order of 10 to the 80. Because then we will be talking about the entire universe, which presumably has something like 10 to the 80 particles, whatever these particles may be, degrees of freedom. Okay? So keep also this in mind. This is adequate to treat that. Of course, it's non-relativistic and it's classical. By the way, at the very end, if you ask me, I will tell you what you obtain if you quantize this Hamiltonian for its spectrum. So you can do the quantum case, not this Hamiltonian, the modified one. Okay, so this is what we. So now we modify this Hamiltonian, and the modified Hamiltonian. No, I'm sorry. Before modifying the Hamiltonian, let me go very quickly through the standard way to treat this problem, and I will go through it very quickly because it's really very, very elementary mechanics. You utilize the fact that there is translation invariant to introduce the center of mass coordinate, which is there, the total momentum. This is the constants of the motion. This is the standard definition of the Poisson bracket. The evolution of every quantity is in this way. I again write prime because I may like to use tau as the time for the evolution. And then you introduce the internal coordinates describing the internal dynamics in the center of mass system. There they are, small q, small y, and they satisfy this restriction. These variables are therefore not all independent. They are not quite canonical variables. I could introduce Jacobi coordinates, but it's not necessary. It's simpler and neater to do that. So you may forget about the fact that these are not canonical coordinates, as you will see in a moment. Then you introduce this small h, which is the Hamiltonian describing essentially the motion in the center of mass system. There it is, and then the total Hamiltonian takes this form, and h, they commute, the small variables commute with the center of mass variable, the variables of the internal motion, and then the equation of motions are written there. This is Newton's equation, and this quantity I consider as functions of this variable tau. Prime indicates derivative with respect to tau. The equation of evolution of the center of mass are written here, and of course the center of mass moves with constant velocity, and the total momentum is a conserved quantity. There they are, and the equation of motions of the internal coordinates are just given by these formulas that you can easily derive. So they are just the Hamiltonian equations for this internal Hamiltonian, even though x and y are not quite canonical variables. So this is a standard treatment of the Hamiltonian, and I've reminded you of this also because I wanted to introduce this Hamiltonian small h, which describes the internal dynamics. And now I just define for you the isochronous Hamiltonian, and the isochronous Hamiltonian is this Hamiltonian here. Now, what is the difference of this Hamiltonian from the previous one? What is well, P is the again the total momentum. H is the Hamiltonian describing the internal motion. This B is purely a normalization constant I put in because I'm a physicist, not a mathematician. A mathematician would not put it in because it would deal with numbers. But this is just for dimensional reasons. It plays no role whatsoever. And of course, it shouldn't be 0. So, and now you see we have the square of this. And then we have added this omega square q square, where omega is an arbitrary real number, and of course it will be connected with the period by this formula 2 pi over omega. And so this is a new Hamiltonian, and we claim, I will show to you that all solutions of this Hamiltonian are periodic with that period t. So this is an isochronous Hamiltonian. And I will also show to you that the dynamics predicted by this Hamiltonian over times, short with respect to this t, is essentially the same as the original Hamiltonian. So this I will show you in a moment, but accept for a moment that I can show this to be true and reflect on the implication of this. The case t equal 2, I will show you an example if I have the time. But think for a moment about this example here, n equal 10 to the 23, a macroscopic body. I can choose omega as I like, so I can choose t as I like. I can choose t, for instance, to be a month. Big T is a month. And then this Hamiltonian here will describe a dynamics which is equivalent to the dynamics of the standard Hamiltonian, describing, for instance, a gas with, say, Lennard-Jones forces, more or less in producing the same dynamics over time short with respect to a month. So for, a few seconds, it will be the same dynamics. So, but that dynamics is the one that subtends the whole of statistical mechanics and thermodynamics. So it will have the usual phenomenon of the macroscopic error of time. If you start from any state far from thermodynamical equilibrium, the system will approach thermodynamical equilibrium. The entropy will keep growing, and you will arrive at thermodynamical equilibrium, and you will stay there. And this may happen within, a few microseconds. And so you had this big T, which is a month. So the dynamics will be the same until then. But on the other hand, with the new Hamiltonian, you know that after a month, the system goes back to the original state. And the original state may have been a state very far from equilibrium. So this is what happens. It's somewhat remarkable. It's even more remarkable if we take 10 to the 80. So if we are talking about the universe. Suppose I look at the Hamiltonian describing the whole universe. Some cosmologists tell me that a description of the universe with classical non-relativistic dynamics is pretty good. Okay, so we describe it with this Hamiltonian instead of the other one. Maybe it's pretty good if the period there is sufficiently large. Say, let's take a period of 10 to the 50 years. 10 to the 50 years. Then presumably the dynamics predicted by this Hamiltonian is the same as the one predicted by the usual Hamiltonian over times of the order of 10 to the 10 years.
Why it is so?
What?
Why it is so? Is it obvious?
No, I will prove it. I said accept that. I will prove to you that the dynamics are the same. I proved it before for the other cases, but I will prove it. But I just say, let's jump ahead and say the conclusions, because maybe you want to leave this time. Well, then this will mean that you cannot really be sure that the real Hamiltonian describes the universe is not this one and not the other one, with 10 to the 50 years, the period. Except that if it were to be this, the consequence would be that 10 to the 50 years from now, I would be giving this talk in front of you again. Not only that, but 10 to the 50 years ago, I would already have given this talk. And this is physics, it's not metaphysics. I mean, this is what this Hamiltonian predicts, and as I say, you cannot really, in terms of physics, be sure that this is not as good an Hamiltonian as the other one. I don't believe that this is the good Hamiltonian, but it's a belief. But physicists say that, what is important is what your model predicts and compare with reality. So you can have a model like this which is consistent with reality just as the one with the other Hamiltonian. Okay, now let's prove this result.
What's the Hamiltonian that describes Francesco Calogero?
Well, it's part of the, if you have an Hamiltonian with 10 to the 80 particles that describes the whole universe, you and me will be part of it as physicists. If you are a metaphysicist or a religious person, you may disagree. But if you are a physicist, that you are part of that. At least I believe so. That's physics. It's,
Well, then I ask you, what is the Hamiltonian that describes you? You are the one that believes this.
what is the Hamiltonian?
Yes.
Well, it's I know that there is an Hamiltonian that describes this. What it is, it's a different matter. It will be maybe a good model is to have many particles which interact with forces. As I say, the cosmologists will tell you that this is a pretty reasonable description of the universe. And if you want to go to biology, I don't know, maybe you need quantum mechanics, and so you have to go beyond. You probably don't need relativity to describe your Hamiltonian. You have, 10 to the 26 molecules which interact. In describing your Hamiltonian, you probably don't need, quarks. You can do it pretty well with molecules and the interaction among them, so you can write this Hamiltonian. Not too hard. What is difficult is to find the solution. But it's very easy to prove that the solution exists. I mean, if you just describe the interaction among molecules with, say, Lennard-Jones, which is a reasonable representation, then you easily prove that it exists for all time. So there is such a Hamiltonian. Of course, you may want to put in the soul and so on, but then that's not physics, that's metaphysics. I'm talking about physics.
Couldn't you argue that what you are saying is that you're arguing against the validity of classical Hamiltonian mechanics on the long time scale?
Why am I arguing against it?
Of course, we start from the belief that classical Hamiltonian mechanics is valid.
Yes.
Time scale.
Yeah.
And then you get to this rather counterintuitive consequence.
Well, but then that means that your intuition is wrong, not that, because what is the alternative? You say I am not putting in quantum mechanics?
Well, something along that line.
Well, I will show you that this Hamiltonian, you can quantize it. So what's wrong with this? It's an Hamiltonian. You can trick it classically or quantum mechanically. I'm not putting in relativity. Well, I'm not sure this cannot be extended to relativity, but that, yes, it is non-relativistic. But if your concern is about an Hamiltonian that describes yourself, you don't need relativity for that. You are a non-relativistic person. Most of the time, I think. So, if that is it, so it's. I think it's the intuition that is wrong. And the conclusion here is that you have to accept that there may be an Hamiltonian which describes a system which is isochronous, provided the period is long enough, which is just as compatible with what you observe as the usual Hamiltonian. I mean, you should believe into that this Hamiltonian written here is just as good, so to say, as this Hamiltonian written here. And this Hamiltonian written here is what is behind a large part of physics. Okay? All right. Now, I'm sorry I'm going over time, but I have to prove this result.
But that contradicts second law of thermodynamics.
No, it doesn't contradict the second law. I mean,
Entropy should increase.
Yeah?
Entropy should increase.
Well,
If you're a physicist.
no. This has to do with this great debate about Boltzmann and company. Maybe I can, first of all, tell you that even with the usual physics, you have a problem there, because I imagine, believe in the theorem of Poincaré. That's a theorem in mathematics. And Poincaré tells you that if you have an Hamiltonian system, which is confined motion, there are the Poincaré recurrences. So if you start from any initial value, you will come arbitrarily close to it after a sufficiently long time. Now, the point there is how long is the time. I will say something about that. But you come arbitrarily close to that. So the entropy has to go back to be arbitrarily close to the initial entropy. What is the way out from this usually in ordinary mechanics? Well, the point is, if you compute the Poincaré recurrences, you find out that time required is so enormously large. It's not 10 to the 50 years. It's 10 raised to 10 to the 23 or something like that for a macroscopic system. So it is, so to say, inconceivable. But that is contained in the equation of the Hamiltonian. So this has to do with, yes, the second principle of thermodynamics is not really compatible with Hamiltonian dynamics. In our case, it's more evident because we have, in a way, constructed with this Hamiltonian here a case in which a Poincaré recurrence is realized, and there are two differences with the Poincaré recurrences here which make the result stronger. First, the recurrence is exact. So you don't go arbitrarily close to the initial data, but exactly at the initial data. And second, you can engineer that this happens after a fixed period of time t that you decide by writing the Hamiltonian, rather than this inconceivably large that it is connected with the Poincaré. But anyway, you know, what I'm going to show you is a theorem. It is not something that I can argue about. So it is true. I mean, there is no question that this Hamiltonian predicts an evolution which is periodic, and I will show you that indeed it is an evolution that will resemble the evolution produced by the standard Hamiltonian, in which presumably you believe, which is that one here. Okay, let's go through this very quickly. Anyway, the proof is always very analogous. You just write, well, sorry, you write the equation of motions produced by this Hamiltonian in the standard way, and here they are for big Q and big P, and they essentially, you see, this Hamiltonian is essentially for big P and big Q just an harmonic oscillator shifted. Remember that when I look at the evolution of big P and big Q, H is just a constant of the motion. In fact, H is a constant of the small h is a constant of the motion. So the evolution of big P and big Q, it's written here. It's just you know, oscillatory. That it is. And then you write down the equation of motions for the internal coordinates, which are here. You just derive that from that Hamiltonian, and you observe that you have this phenomenon, and so the solution for x will just be the previous solution produced by the, so to say, usual Hamiltonian, but with, because it's that corresponding to the internal dynamics of your system, with in front this term here, and so you can incorporate it, but the final basic formula is this one. This is the x tilde and y tilde are the evolutions predicted by the tilde Hamiltonian. X and y are the evolutions predicted by the non-tilded small h Hamiltonian, the one describing the physics in the center of mass system of the usual system, and tau is just this explicit function of time, where big C and T0 are two constants that depend on the initial position of the center of mass. This is exact. I mean, this is it's compute. It is, and then the implication of this is, of course, this is what happens in the omega equals 0 limit. Let me jump this. But if you look at a time evolution starting from tau bar, an arbitrary initial datum, over a time t minus t bar, which is small with respect to big T, then you see that tau of t becomes linear in t, and so the evolution that given by the new Hamiltonian is essentially up to a shift in time, that produced by the original Hamiltonian. You see, because tau has become a linear function of t over short intervals. So I've proven for you the statements that I have made. And you have then this phenomenon of transient chaos, because if you take t sufficiently large, and if your system is one given chaos, you will have something very similar to chaos over some period of time. Of course, it's not strictly chaos, because chaos to be defined requires an infinite time, but it will be something that physically it will be like chaos, and therefore over that period of time entropy will increase, you will approach thermodynamic equilibrium, but then eventually you go back in time in a way, you oscillate over time. Okay, well, this is a simple example. Is you take the two-body problem, and in the case of the two-body problem, with just harmonic oscillator potential that it is, it can be omega squared could be positive or negative. If it's positive, you have an harmonic oscillator. If it's negative, you have a repulsive oscillator in which the particles fly away. Then you modify the Hamiltonian in the manner that we suggest. The modified Hamiltonian is just written here, and you can solve explicitly, and this is the explicit solution. You see, you have this big omega, which is the one that gives the periodicity. But if this term, big omega times t, is very small, then this will behave just as t, so just as the original Hamiltonian. And for instance, let me show, it's from the book. If you take big omega to be 40 times smaller than small omega, this is the solution that you will see. And you see, this part here is just mimicking the original Hamiltonian, a harmonic oscillator with this frequency 2 pi over small omega, but then the overall dynamics is in fact periodic with this larger period, and there are some moments in which things change very much, and this is the time when it so happens that q dot of t is 0, so when the center of mass somehow comes back. At those times, the dynamics will look very different. And okay, this is, I guess, well, this is the other case in which you had a repulsive. You have omega squared to be omega imaginary, omega squared negative, then you have a potential like this, the particles fly apart in the two-body problem, but after you have changed the Hamiltonian, you still have a periodic system, and the trajectories are like this. This will be the region in which it flies apart, but then it has to come back. And this is, I think, over almost 2 periods what you will see. Well, the quantum case I will not go into, and these are the references. Okay, I apologize for having gone over time. Yes?
Well, it's more a comment than a
Yes.
question. Coming back to the last example, you have an enormous equilibrium manifold, it's codimension 2, because you can put the big P equal to minus the conserved value of little h divided by P, and then you put your big Q equal to 0, and if that's your initial condition, then you get no motion at all for all of the degrees of freedom, because you're basically in the origin of the harmonic oscillator variables, and they steer the oscillation that you have in the other variables. So if you go sit in this equilibrium, there's no motion at all. Now this is a huge part of phase space. It's codimension 2. And I think this is the analog of what you have in the situation with Taimanov and Bolsinov. Very likely, these commuting Hamiltonians that you may be able to construct, although there is no general theorem there, of this manifold will get singular as you go to this special manifold. And this would also explain why, in the other example, where you have a linear flow on this special codimension 2 set, you can have chaos. It's because the commuting Hamiltonians in the huge ambient space will get singular as you approach this particular, still very big part of phase space. And that's all consistent with what you're telling us.
Yeah, of course. Everything is.
But it's something for global analysts to sort of push this through, of course. It's probably not easy at all yet to find these commuting Hamiltonians in some more or less explicit form of this big codimension 2 part of phase space. It's not. It's probably true, but it's not by no means in the box.
No, of course. But the point is that it certainly will be impossible to construct them explicitly in any complicated case. But the point is that they exist.
Well, who tells you? I don't know any theorem in the box that tells you so. I mean, locally, of course, there is the flow box lemma that tells you can always find as many commuting Hamiltonians as you please.
Yes.
Right? Locally, any system, any
Yes.
even
And
you
we-
not restrict to Hamiltonian system.
Yes,
Just the vector field.
And we can
You have
prove.
the flow box lemma, and then there you can take just the coordinate to be the flow along this vector field.
Yes.
So locally, you have super integrability. The whole problem is a global analysis problem, and I'm not aware of any place in the literature where what you are saying should be true has been proved. Although I believe it is true of this exceptional manifold.
So what you are saying is that we may have constructed a system that is isochronous, so all its solutions are completely periodic. However, this system, you say you are not sure that this is Liouville integrable.
That's right.
Yeah. Well,
Because
I think.
it's the global aspect that devils.
Well, but we can construct the constants of the motion. explicitly. They are there, they are explicit, but they are explicit in terms of the solution of the original model. So the whole issue is that if the original model is globally, has solutions which are globally defined for real time, then this constants of the motion exists. I mean, one has them, they are, so there is, you can construct them. Of course, you can construct them using the solution of the model, which if it is very complicated, you will not know, but you know that they exist.
Well, I don't know where the existence theorem in the literature occurs. That's what I keep saying.
The existence theorem of the solutions? No, this is...
That there are such Hamiltonians that are defined globally of this exceptional manifold.
Ah.
Certainly will not be.
Yes, well,
you know,
the existence theorem is here. It's in, it's very easy to prove, but Francois was reluctant to put it there because he said it is so well known. But oh, what happened? Somehow it's, I don't know what I did, but something terrible. Anyway, it is we give a proof. We give a proof in this paper here, in the one that is already published. Well, the one is called Short Time Poincare Recurrence in a Broad Class of Many-Body Systems. It's on the Journal of Statistical Mechanics, and it's out, and there is a proof of this fact. I mean, we construct the constants of motion explicitly in terms of the solution. Explicitly in terms of the solution of the original model, which all you know they exist, but you don't know how to find. So it boils down to the fact that the solution exists, and that is easy to prove in dynamics, that a system with some feature, you should of course have no singularities, but for instance take a model with particles that interact with Lennard-Jones potentials and harmonic oscillators or any confining potential, then you can prove that the solution exists globally for all time. Of course, if you have 10 to the 23 particles, you won't be able to write that solution, or even if you have, 3. But it exists, and once it exists, using it, you can construct the constants of motion for the new systems. You don't know them explicitly, but in mathematics, you prove that it exists.
Well, you need to produce as many Hamiltonians as there are degrees of freedom in so
Yes.
that the Poisson commute. And
Yes.
that seems to me quite a task.
No. The fact that they Poisson commute is, again, if you have a system of n degrees of freedom and you construct 2n minus 1, then I think there is a proof in Arnold's book that n of them have to Poisson commute. It has already been proven. I haven't looked it up. I've taken it for granted.
Well, did you discuss this with Arnold? I would be very curious what Arnold thinks about this whole business.
It's very difficult to discuss with Arnold, I warn you. I
Well,
tried.
take Weinstein or Marsden or Dusa McDuff, one of these
maybe,
global symplectic people.
Maybe.
You know, I mean,
Well,
I wouldn't
these
be surprised if
papers
they're
are
very
now in the literature. I mean, they're open, so people can read that, object, or discuss.
So yeah, I have a comment which maybe partly answers Simon's question. There was actually a continuation of Taimanov-Bolsonov paper by Leo Butler, who is now in Edinburgh actually. He proved that any dynamical system, I think, can be embedded into a completely integrable system. But the thing is, and that's the main thing, smooth, the integrals are smooth. C infinity, that's the thing. There is a big difference between integrability in analytic category and in C infinity category. And that's the one of the lessons actually of Bolsonov-Taimanov example. I mean, it's a system when these extra integrals you have, one of them must be analytic. That follows from Taimanov result actually. So, but Leo Butler paper is quite ineffective. It's really in existence, and I would say you wouldn't be probably satisfied by reading his paper. But there is this kind of analytic results, infinity results.
Okay.
And another thing which is I think, much older result that any system can be, if I'm correct, any system can be realized as subsystem in Hamiltonian system by adding enough extra variables. You can realize any system as subsystem in Hamiltonian system. So if you allow yourself to add variables, then the difference between, roughly speaking, between integrability and non-integrability, Hamiltonian and non-Hamiltonian, essentially disappear, because you can always, that's the kind of thing which people discovered first, I think, in non-holonomic mechanics, because non-holonomic mechanics is not Hamiltonian, and they find that they realize that by adding extra variables, you can always assume that this is a kind of Hamiltonian.
Yeah. Well, this is why I sort of emphasize this difference between extending and modifying. But in
You
the sense
extended,
the
of course,
two
in
are
a
not
very
too
special
different,
way.
because you use the fact that the center of mass motion is trivial, and then all I have described to you is so elementary that cannot be a major discovery. But nevertheless, it is an explicit implementation of this of these facts. I mean, which don't contradict anything. Yes. Except the second principle, but that was known, that the second principle is incompatible with Hamiltonian dynamics, the second principle of thermodynamics.
I have a short comment. I know another big number. It's 10 to the power 300. That's the dimension of Hilbert space of a quantum computer with 1,000 qubits. That's it.
On that note,
Let's thank our speaker again.